So let's do that with the other. So basically, we are working towards the material for the last 2 weeks. I never found one problem that is suitable to everything that I want. So I think last time we make up a problem and we did something in class now. So let's try to do something similar. So, and then Thursday, if you want, we can talk about exactly what you will work on the exam. Okay. All right. So let's review your problem. So last time we did like a structure with a log that we need to find the normal stresses, shear stresses, and do the design of the bolt correction. No? All right. Okay. So today, let's see. I'm going to look at what will be. I'm going to look at the good man. If you remember the good man. Criteria, which actually you have what? So if I do a quick summary, then we can make up a problem. But basically, the Goodman criteria, we say that if we have a curve, so basically, if we plot on the x direction the alternating stresses, and on the x median, then we define two of them. So if we look at here, the endurance stress with respect to the ultimate stress, and it will go through this line over here. This is known as the Goodman-Ferrer criteria. Okay, and we say that the equation will be the alternate divided by the endurance plus the median or the average divided by the ultimate. This needed to be equal to 1 over n, where n is the safety factor. Okay, what else do we have over here? What are the equations we had? Yeah, that the sigma n was equal to sigma max. So basically, the average is the mean divided by 2, and that the alternating divided by 2. Okay, so given that information, let's say we can come up with some type of problem. All right, so let's say here, let's consider a cantilever beam that is attached at the free end to a shaker, okay, let's say. Okay, so again, I'm making it up. So let's say over here, so if I do some type of plotting, Let's say this will be our cantilever beam. I'm going to make it a bit longer, so I have more space to do a figure here. Okay, that doesn't mean it's that long. So let's say, maybe you can give me values. What do you want the length of the beam to be? Anyone?
25.
25 what? Meters, inches, feet?
Inches.
Inches, that's fine. Okay, so now let's say this is attached here to a shaker. I mean, you all know what a shaker is, no? Basically, it will be a machine that is just going up and down. Okay. So let's say the shaker creates a force. How much? 200 pounds, okay. Yeah, we're gonna make that. Now, we don't need the material, but we need to look at the cross section. We're just thinking about, so the cross section of the beam, let's say, can we make it rectangular? Since I started, didn't matter, but. So what dimensions you want for the beam? Okay, so I put 2 and then what about this one? Let's say 4 by 2 is okay. I wanted to add another force, but I don't want to add too much, okay? Might take too long. So now for the good one, let's say that we know here. So let me take some data from another problem here. The endurance, let's say, is 20 KSI. I'm taking this from a previous example we did in class. Okay, I have the. Okay, the ultimate will be 82 KSI. Okay, and I'm going to say here, whatever, let's say that on this beam, whatever, consider that in order to run the cables, all right, you have a which is going to introduce a stress concentration factor due to the hole. Whatever, I'm going to make it here. 1.7, okay? Due to okay, so basically what's going to be the problem? So you want to use, let's say, a safety factor of how much? Go ahead. 2.5, which is actually traditional for structural. So safety factor 2.5. Our question will be what? To see if, let's see if this structure is safe considering the Goodman criteria. No? So question, determine if the mechanical structure is safe according to the man-fellow criteria. Okay, so what do we need to find out here? What is the first thing? So first, where is the location? If this beam is going to break, what is the critical location where it might break? At the wall, no? Yeah? I mean, he might be detached, no? But if it's going to fail, it's going to fail at this location, no? That's where the stresses should be maximum, no? So let's say critical location. At the wall, where the stresses are the highest. Okay, so what is the general equation for, so let's say if you want, since now we become really good at this, let's say this is y and this is x. Okay, so this will be what then? This, let's say this will be y and z, no? Okay, so the stresses we need to calculate will be in what direction? Y or z? The normal stresses should be on the x, no? And this should be equal to what? M should be the moment about which axis? Due to this force here moving up and down, okay, this two shaker here, 200. Is this will be rotated about which axis? Z, no? Yeah. So will be the equation will be mz. Now the stresses will be changing with respect in what direction? On the y direction. And the bending will be about which axis? Z. So you see, you don't need to memorize the equations once you have an understanding. No? Okay, does everything make sense on the equation? Okay, so maybe let's see, let's do here the structure. We have this. So this is, let's say this is B equal to 4, H equal to 2. I'm going to try to keep it symbolic, okay, for as long as I can. So in this equation, where in here we know that, okay, natural axis, okay? So in this case, we know it's in the middle, okay, symmetric. So what will be then the distance? 1, correct, H divided by 2. Then what will be IZZ? Then 1 BH cubed, whatever the value would be. And then I mean, the force here is up and down, so I'm going to make it, let me make it this way. We say is 200. This is L, so if you wanted to be very detailed, if you had to do here the bending diagram, what would be the bending diagram figure? The maximum of the root now. What should be the value of the root of the moment? F times L now. I mean, I hope this is clear now, no? Okay. Let's say here NZ will be F times L. Okay, and this force here, due to the shaker, so this force over here, what will happen now to the load? Due to the shaker, what's going to happen to what's going to be the motion of the tip? Right, so it's going to be sinusoidal. Let's say it's going to be alternating, no? This is time. And if you want this one, they call it sigma x, but will be really alternating.
Should the moment also be alternating from positive to negative? When the signs of the moment be alternating?
Correct, that's exactly what we're doing. So that's why it's going this way, positive, negative, no? That's exactly what I was trying to be next to show that, okay? Okay, so in other words, what are we gonna have here? Our alternating stress really should be equal to what? The sigma x, and should be equal to, like you mentioned, the moments will be alternating between positive and negative, which will be minus f of mzy divided by zz. Maybe I'm going too fast over here. Yeah, I mean, that's fine. So it should be equal to what? Plus minus f times L times h divided by 2 divided by 112. So maybe I'm doing too much symbolic here, no? Let me call here, forget the alternate, keep calling sigma x, sorry, because otherwise we're going to lose some understanding. I will do that later in a second. It's just for your understanding, yes? Okay, so what about you start giving me a value, because this is starting to get too complicated now. So this will be, how do you say, 200 times, what was L? 25 times 2 divided by 2 divided by 112 of 4 times 2 to the cube. Okay, somebody else can double check, but I trust 1875. PSI. So I'm going to redo here a figure, okay, because you know I love figures. So basically, what does that mean? That here we're going to have sigma max equal to 18.75.
18, like 1,875, not 18.7.
Okay, so okay.
That's what you got too, right?
So 1875, no, without the point.
No point.
So here the same thing, okay? Sorry for that. And then here will be, this will be the minimum value, which will be negative 1875. Yes. Okay, so in this case, if you remember the figure, here, this is what is known as the alternate. All right, so from the equations I gave before, what will be the medium or the average stress? From the figure, it should be zero, no? But if you do the calculation, it should give you zero. So this is going to give you zero. The alternating is going to give you what? 1875. Okay, I did it very simple here because you don't want it to complicate it.
Eighteen seventy-five or 1075?
1875, they say. So 1875, no? No, you're right here. I know why he's saying that. My writing. Okay. Okay. So now, what is something we don't have to forget? What did you say was happening because of the hole? This hole is going to create a stress concentration, no? Okay?
Negligible for the inertia now, like we're ignoring the area.
What do you mean, negligible?
Are we ignoring the area of the circle?
Ah, the one inertia, yes, we're ignoring it, okay?
Okay, so it's just there to produce.
Yeah.
Okay.
Yeah. All right. Depends how detailed you want to be, okay? But if you want to do a first design, that's why we do it, okay? This KT should take that is the kind of stuff that it should be taking that into consideration. No, good observation, okay? So really, this concentration factor here, since you mentioned this stuff, how do you think it's obtained? You do the stress like if it was without the hole, and then you do the stress just considering if it was like you remove the thickness of the diameter of the hole, no? You just consider that will be effective. You divide one by the other, depending on the size of the circle, you will get different concentration factors. Okay. Does that make sense? All right, so here we go. So now let's say.
Each of the one that's super tight.
Yes. Yeah.
In the stress calculation using the whole as part of the moment of inertia, does that mean you wouldn't need to do a stress concentration using the factor?
If you were removing the diameter of the hole,
Yeah.
yes. That's basically what all this stuff is doing. All right, so let's say now, we call it the stress concentration factor KT equal to what? 1.7 due to the hole. And the hole, let's say, was put there into the beam in order to run the wires for the shader, whatever you want. Okay. So we have then, let's say, the alternating would just become then KT, or the new bar, let's say Q bar alternating would be this one here, which will be 1.7 times 1875 would be how much? $2,187.5. Okay, and let's say one more time now. Next, we call him the Goodman Taylor criteria that we defined at the beginning, which is what? Sigma A bar over S endurance plus sigma median over S ultimate equal to 1 over N. Or the figure. Again, you know that I like figures. Oh, I don't know why I did this one so long. In this case, this is 0, so our Goodman line is going from where to where. Ultimate here, which is we don't even need, but we say was equal to 82. And here this value was here. Oops, you see? But down here, this is we put that value here to be how much? As endurance 20, yeah. Sorry for my notation. So that figure again, leave some space on top of the figure, okay? So in this equation for us, what is sigma m? 0, no? Okay. So really for us, this becomes what? Sigma bar A over S endurance needs to be equal to 1 over N. So first, without even looking, is it going to be safe or not safe? What do you think? Find out. So this would be what? 3,187.5 divided by how much? S endurance, we say, oh, it's huge. It's very, very safe, no? How much was S20? Sorry, I keep with my 82, I don't know. 20, 10 to the 3. So what do you get for this?
0.159.
0.159. Okay, so let's go here, let's do this. So let's see. Here, maybe I did a mistake. What should I have put maybe here instead of equal? Because what would be the failure? Okay, let's do it this way. Okay, so let's see. We have this. This should be equal to 1 over N. So now, if you solve for N, what do you get? Maybe that's a bit easier way.
6.27.
6.27, which is larger than our 2.5, no? That we require. So what can we say at the end?
It is like the
Safe design, no? Sense? Okay, you see, it's better to do this type of plans that just once come straight from the book, no, I guess. Yes.
For sigma m, if it has not been 0, do we have to apply the KP for that as well?
Yes,
Sigma,
correct. So originally what I wanted to do, but then if you want, what about you and do it? I think it would be a good practice. So now for practice, repeat the problem. Considering, let's say, a constant force of how much you want to put? 180, okay. 180 pound applied. at the center of the list. So basically we have the same thing, our shaker here. F equal plus minus 200. But let's say we have here force P of how much we say 180. So now what's going to happen? What is this 180 force going to produce? It's going to produce that sigma sub n is not going to be zero, no? You're going to have a constant one. But everything else should be the same, no? So here, the only reason I did not do it is because what is the thing you're going to have to do over here? It's pretty straightforward, is it? But you first need to find what is the reactive moment over here, no? Yeah. By doing what? I mean, if you start from this end, I mean, you still have, I mean, figure out you have one or two cuts, no? You want me to give you some time to do it on your own and we check it, or you want me to do it? Well, I'm going to give you some time to do it, okay? So just call it. Before I give you the time, do you have any question about what needs to be done? Everything else is the same. The only thing that's going to change is what? You need to find what will be the new M over here. Because of this P over here, now you're going to have a sigma sub n that is not going to be equal to 0. All right. So I'm going to give you about 15 minutes to do it. And if you have a question, you can call me and I'll go by your side and answer it. You know, resume the request. So maybe.
I can have that done in 15 minutes.
Do you know where the number started recording? Did I do everything else on the recording or not? Okay, maybe let me just show the picture then on the recording. Yeah, so backwards. Right. All right. So any question about what we did today? What is expected from you on the exam?